Hey Bob, I've been going through the February 2026 papers and there's a lot to unpack. It feels like a particularly rich month across multiple fronts. Error correction, networking, algorithms, even some philosophical debates about quantum advantage. Where would you want to start?
You're right. It's a dense month. I'd actually start with what I think is the most headline-grabbing result, the Pinnacle Architecture paper from Webster and colleagues. They claim you can factor RSA 2048 integers with fewer than 100,000 physical qubits using quantum LDPC codes. That's roughly an order of magnitude fewer than previous estimates. If that holds up, it dramatically changes the timeline for when quantum computers become a cryptographic threat.
That's striking. Previous estimates were in the millions of physical qubits for that task, right? What's the key innovation that gets them there?
Exactly. Prior surface code-based estimates were often in the millions. The Pinnacle architecture leverages high-rate quantum LDPC codes, which encode many logical qubits per physical qubit far more efficiently than surface codes. They also carefully co-design the fault-tolerant architecture around these codes, minimizing space-time overhead throughout the computation. It's a full-stack design, not just a code choice. The assumptions include a physical error rate of 10 to 3 and a reaction time of 10 microseconds, which are aggressive but not unreasonable targets for near-future hardware.
Speaking of LDPC codes in practice, there was also the paper from Dasu and colleagues at Quantinuum demonstrating beyond break-even performance with high-rate codes on their 98-qubit Helios processor. How does that connect?
That's a really important experimental companion to the Pinnacle theoretical work. The Quantinuum team demonstrated that their so-called iceberg codes, which are high-rate codes encoding many logical qubits simultaneously, actually outperform unencoded qubits on a real trapped ion machine. They achieved beyond break-even performance with up to 94 logical qubits, and even ran a quantum simulation of a 3D XY model of magnetism in a partially fault-tolerant way. The key point is that trapped ion systems offer the long-range connectivity that high-rate codes demand. This is a concrete proof that high-rate codes are viable today, not just in theory.
There were several other error correction papers this month too. The RISQL paper from Yang and colleagues caught my eye. They're proposing a whole instruction set architecture built around qLDPC codes. How does that fit into the picture?
RISQL is a really clever systems-level contribution. The insight is that even if qLDPC codes give you a smaller footprint, you still need an efficient way to execute real algorithms on them. They introduce what they call a complex instruction set quantum computer, CISQ, that embeds specific algorithmic subroutines like quantum arithmetic and magic state distillation directly into co-designed qLDPC codes. They target neutral atom platforms because of their reconfigurability. The result is a 2x to 7x footprint reduction compared to surface code architectures for realistic error rates, while keeping space-time costs competitive. It's essentially showing that qLDPC codes can be practical compute modules, not just memory.
And there was also the self-dual stacked qLDPC codes paper from Liu and colleagues, which seems to address the challenge of implementing logical gates on these codes. What's the novelty there?
That paper tackles a persistent headache with qLDPC codes. While they're great for storage, performing logical operations on them is hard. The trick the authors introduce is stacking two non-self-dual qLDPC codes together to create a self-dual code. And self-dual codes have the nice property that transversal Clifford gates are naturally available. They construct several families, double-chain bicycle codes, double-layer bivariate bicycle codes, and others, and show numerically that these can achieve significantly reduced logical failure rates. It's a constructive solution to what has been a major obstacle in making qLDPC codes computationally useful.
On the fault-tolerant interfaces side, there was a paper from Christendal, Forzi, and Goswami on fault-tolerant interfaces for quantum LDPC codes. What problem are they solving?
This one addresses a subtle but important problem. How do you move quantum information between different levels of error protection without blowing up your resource overhead? Previous approaches required polylogarithmic space overhead for this kind of level-changing operation. Christendal and colleagues show you can do it with constant space overhead by gradually lowering the protection level while simultaneously increasing the number of code blocks being decoded together. It's a clever way to avoid error pileup at the interface. This matters enormously for practical fault-tolerant architectures where you need to shuttle information between different code blocks.
There was also interesting work on combining error correction with dynamical decoupling. The paper from Kasatkin and colleagues. I've always wondered whether these two approaches play well together.
That's a great question, and the paper gives a nuanced answer. The key insight is that naive physical dynamical decoupling can actually conflict with the encoded subspace of a QEC code. Their solution is to implement decoupling logically using normalizer elements of the stabilizer code so it's compatible with the code structure. They derive closed-form fidelity expressions for hybrid protocols and show that the hybrid approach beats QEC alone only under specific conditions, roughly when the decoupling suppresses errors that the decoder would otherwise fail to correct. They validate this numerically on the Steen code and a 13-qubit code. The takeaway is that co-design of the code, decoder, and decoupling group is essential. There's no free lunch.
Shifting to the experimental networking side, the paper from Liu and Pan's group on quantum repeaters was remarkable. They seem to have crossed a critical threshold.
Yes, this is arguably the most significant experimental quantum networking result of the month. The team at Pan's group demonstrated memory-memory entanglement over 10 kilometers of fiber where the entanglement can be established and maintained faster than it decoheres, which is the fundamental bottleneck for quantum repeaters. They used long-lived trapped ion memories, an efficient telecom interface, and a high-visibility single-photon entanglement protocol. As a direct application, they demonstrated device-independent QKD over 10 kilometers and showed a positive key rate over 101 kilometer in the asymptotic limit. That 101 kilometer figure extends the achievable distance by more than 2 orders of magnitude compared to previous memory-based approaches. This is a genuine milestone toward a quantum internet.
Complementing that, there was also the entanglement swapping demonstration from Craddock and Namazi's group using deployed New York City fibers. That seemed to take a very different approach.
Right, and the contrast is instructive. Where Pan's group used trapped ions and sophisticated quantum memories, Craddock's team used warm atomic vapor cells as entanglement sources. The clever insight is that warm vapor cells produce naturally indistinguishable photons without needing shared lasers or optical frequency references between nodes, which is a huge practical advantage for real-world deployment. They achieved nearly 500 entangled pairs per second while maintaining CHSH violation over 17.6 kilometer of deployed NYC fiber. It's a more scalable and commercially accessible approach, even if it doesn't yet match the distance or memory capabilities of trapped ion systems. These two papers together paint a picture of the field converging on real-world quantum networking from multiple directions.
And then there was the Berlin teleportation experiment from Borowska and Namazi's group, teleporting over Deutsche Telekom's actual deployed fiber infrastructure. What made that notable?
What's particularly impressive about the bichromatic teleportation experiment is the real-world engineering. They achieved 90% average teleportation fidelity over a 30 kilometers deployed fiber loop in Berlin, using commercial components at a telecom data center. Crucially, they demonstrated compatibility with co-propagating classical C-band traffic in the same fiber, meaning quantum teleportation can share infrastructure with live classical data channels. This wavelength division multiplexing compatibility is essential for any practical quantum network deployment because you can't realistically dedicate entire fiber cables to quantum signals. It's a proof that quantum networking can piggyback on existing telecom infrastructure.
Let me ask about the topological quantum computing paper from Lyons and Brown. They claim to show that anyon-based quantum computing is fault-tolerant in a modern error correction sense. That seems like it closes a long-standing gap.
This is a beautiful theoretical result. Kitaev's original topological quantum computing proposal relied on maintaining a ground state at zero temperature, which is physically unrealistic. Lyons and Brown show that you can instead actively correct errors using noisy circuit elements and still achieve fault-tolerant universal quantum computation by braiding anyons. They prove a threshold theorem for this scheme. Below some noise level, you can make the failure rate arbitrarily small. This bridges the gap between the elegant physics of topological quantum computation and the practical reality of noisy hardware. It's a significant conceptual advance that validates topological approaches within the modern fault tolerance framework.
Related to that, there was a paper from Long and colleagues on implementing universal gates via double braiding in SU2K anyon models. How does that connect?
That paper provides a concrete computational scheme for topological quantum computing. The double braiding approach is interesting because it's topologically equivalent to manipulating fewer physical anyons than naive braiding would require. Specifically, a 3-enyon encoding of a single qubit only requires physically moving one enyon. They use a genetic algorithm-enhanced Solovay-Kitaev approach to synthesize standard single-qubit gates and approximate CNOT class 2-qubit gates. The numerical results are quite convincing that double braiding in these enyon models can support universal computation. Together with the Lyons-Brown fault tolerance result, you have both the theoretical foundation and a practical gate synthesis strategy for topological quantum computing.
There was a fascinating experimental result on the surface code teleportation transition from Zhu and colleagues using a 125-qubit superconducting processor. The magic injection angle was a surprising element. Can you explain what's going on there?
This experiment is beautiful because it connects topological quantum matter with practical quantum computing. They demonstrated robust teleportation of logical states encoded in surface codes with distances up to 7, and they mapped out a teleportation phase diagram by tuning entangling gates. The really surprising finding is that you can boost the entangling threshold, the minimum entanglement needed for teleportation to work, by injecting magic resources beyond the Clifford regime through coherent qubit rotations. This restores a duality symmetry of the topological phase. Essentially, magic isn't just a resource for computation. It can also help you use less entanglement to achieve reliable teleportation. It's a beautiful interplay between the two key quantum resources.
Speaking of magic, there were two very different papers on the topic this month. The computational hardness result from Leone, Isett, and Oliviero on the stabilizer polytopy, and the many-body physics paper from Hallam and colleagues on spectral signatures of magic near criticality. How do these fit together?
These papers approach magic from completely different angles and together paint a rich picture. Leone and colleagues prove something quite alarming, determining whether a quantum state lies in the stabilizer polytope, or the set of states that requires zero magic, requires super exponential time, scaling exponentially in the number of qubits. They reduce the problem to 3 SAT on n to the power of 2 variables. This means that quantifying magic for general states is fundamentally intractable, and any magic monotone must be super exponentially hard to compute. Meanwhile, Hallam and colleagues take a many-body physics perspective and show that magic, measured via stabilizer Rényi entropy, has its own correlation length that diverges at quantum phase transitions distinct from the standard correlation length. So magic is a new lens on criticality. Together, these papers say, magic is computationally intractable to assess in general, but it carries deep physical information about quantum systems.
The paper from Proctor, Blumkohout, and Bachevsky, titled The Road to Useful Quantum Computers, seems like a broader perspective piece. What's their main message?
It's a really valuable piece because it cuts through the hype with a rigorous framework. They distinguish between what current quantum computers can do and what's needed for genuine quantum utility, solving scientifically or practically important problems that classical computers can't handle. They trace the history from Feynman and Manin's original vision through Shor's algorithm and quantum error correction, then give an honest assessment of where we are today. The key contribution is a framework for tracking progress, what metrics matter, how to measure them, and what the remaining engineering and science challenges are. It's a sober, expert-level roadmap that complements the more optimistic, experimental results we've been discussing.
There were also two qualitative studies from Doyle, Saifolahi, and Singh on expert perspectives. One on whether we have a quantum computer and one on hype and education. What did those add to the conversation?
These are genuinely useful sociological snapshots of the field. The expert perspectives study found broad agreement that current machines deserve to be called quantum computers, but estimates for fault-tolerant systems capable of running Shor's algorithm at scale range from 1 to several decades. Experts also agreed that quantum computers will remain specialized tools in data centers, not pocket devices. The education and hype paper is equally interesting. It highlights how the hype cycle creates unrealistic expectations that can harm the field's credibility and workforce development. Educators emphasized the need to attract non-physicists by leveraging their existing expertise, and noted persistent tensions in university-industry partnerships around IP and confidentiality. These human and institutional dimensions are often overlooked in technical discussions.
Let me ask about the quantum networking and QKD security papers. There was the Hypercube Quantum Walk QKD paper from Polzoni and colleagues, and also the quantum repeater paper we discussed. How does the QKD work fit in?
The Hypercube Quantum Walk QKD paper from Polzoni, Bianchi, and Conti is a nice theoretical contribution to one-way QKD protocols. The key idea is that security in their protocol depends entirely on the topology of the quantum walk, not on protocol-level details. They show that using a hypercube topology rather than the conventional circular topology provides significantly better eavesdropping resistance and noise tolerance under identical parameters. They also release an open-source Qiskit simulation framework for topology-aware QKD analysis. It's a step toward understanding how the geometry of quantum walks shapes cryptographic security, a topological approach to QKD design.
There was also the qDBFT paper on quantum-secured blockchain from Zhu and colleagues. How does that relate to the broader quantum security landscape?
qDBFT addresses a real gap. Current blockchain consensus protocols like PBFT are vulnerable to quantum attacks via Shor's algorithm, and they also have scalability issues with dynamic node membership. The paper proposes integrating QKD for message authentication between nodes, providing information theoretic security for the consensus process, combined with a consistent hash ring for fair primary node rotation. The experimental results show performance comparable to classical PBFT. It's a practical engineering contribution, though it inherits all the deployment challenges of QKD infrastructure. It connects nicely to the broader post-quantum cryptography conversation.
On that note, there was the paper on quantum attacks on nuclear power plants from Basseri and Waller. That seemed quite alarming in its framing.
It's a sobering paper that takes a forensics-first perspective on quantum threats to critical infrastructure. The key threat they highlight is harvest now, decrypt later attacks, where adversaries collect encrypted data today and decrypt it once cryptographically relevant quantum computers exist. For nuclear power plants, which have decades-long operational lifetimes and legacy OT systems, this is an acute concern. Their probabilistic risk modeling suggests alarming success probabilities for targeted attacks under current defenses. They propose a phased migration to post-quantum cryptography, integrated with existing industrial standards. The two case studies, Quantum Scar and Quantum Dawn, illustrate how quantum attacks could create forensic paradoxes that make incident investigation nearly impossible. It's a call to action for critical infrastructure operators.
Switching to algorithms and optimization, there was the quantum-enhanced Markov chain Monte Carlo paper from Marshall and colleagues at IBM, and also the non-variational MCMC approach from Ferguson and Walden. These seem related, but what's the connection?
Both papers are pushing quantum optimization away from the dominant variational paradigm toward MCMC-based approaches, which is a significant trend. Marshall and colleagues demonstrate empirically that quantum-enhanced MCMC can recover global optima for maximum independent set instances with up to 117 qubits on IBM hardware, with early evidence of a scaling advantage over classical methods. Ferguson and Walden take a more theoretical approach, introducing quantum-enhanced simulated annealing and quantum-enhanced parallel tempering, showing superior scaling on hard Sherrington-Kirkpatrick instances. The appeal of MCMC approaches is that they're inherently noise-resilient. The randomness in MCMC is a feature, not a bug, and they can run in parallel across quantum and classical resources. This is a promising alternative to QAOA for near-term optimization.
There was also the QAOA paper from Mansilla and colleagues on portfolio optimization with XY mixers and trotterized initialization. How does that fit into the QAOA landscape?
This paper addresses a real weakness of standard QAOA. When you have hard cardinality constraints like pick exactly K assets, transverse field mixers don't enforce those constraints, so you need soft penalties that distort the optimization landscape. The XY mixer approach strictly preserves the Hamming weight of the solution, meaning only valid portfolios are ever explored. Combined with Dick state initialization and trotterized parameter scheduling to avoid barren plateaus, they achieve a sharp ratio of 1.81 on backtested data, significantly beating simulated annealing and hierarchical risk parity. The high turnover rate of 76.8% is a practical concern for institutional investors, but the algorithmic contribution is solid. It's a good example of constraint-aware quantum algorithm design.
The paper on quantum advantage in decision trees from Grillo and colleagues took a more theoretical approach to understanding when quantum algorithms actually beat classical ones. What's the key insight?
This is a nice theoretical contribution to understanding the structural conditions for quantum advantage. They formulate single-query quantum decision trees as weighted graphs and show that a high L1 spectral norm of the algorithm output is a necessary condition for quantum advantage over classical decision trees. They then provide heuristics for maximizing this norm and construct functions exhibiting exponential quantum advantage. The graph formulation makes it easier to reason about when quantum algorithms can extract maximal information from a single oracle call. It's foundational work that helps us understand the geometry of quantum advantage rather than just cataloging specific examples.
On the ground state preparation front, there were two interesting papers, the shadow-enhanced greedy quantum eigensolver from Earl and Kochsor, and the adiabatic warm start VQE from Puig and colleagues. How do these compare?
Both papers tackle the same fundamental problem, preparing ground states efficiently on near-term and early fault-tolerant hardware, but from very different angles. The shadow-enhanced greedy quantum eigensolver uses classical shadows to evaluate many candidate gate operations in parallel through classical post-processing, greedily selecting the best gate at each step. The key advantage is logarithmic sample complexity in the number of candidate gates, making it very measurement efficient. The Warmstar adiabatic VQE from Puig and colleagues instead deforms the Hamiltonian gradually, solving a sequence of intermediate problems that track the ground state manifold. They prove a lower bound on loss variance that guarantees trainability away from gap closings. These approaches are complementary. SEGQE is more measurement efficient per step, while the adiabatic approach provides stronger theoretical guarantees about avoiding local minima.
The quantum subspace diagonalization paper from Berent and colleagues seemed to offer a practical improvement for quantum chemistry applications. What's the rotation thresholding idea?
Quantum subspace diagonalization methods are promising for early fault-tolerant quantum chemistry because they avoid the deep circuits of full quantum phase estimation, but they suffer from ill-conditioned generalized eigenvalue problems that are highly sensitive to noise. The key innovation in this paper is applying eigenvector-preserving rotations to the generalized eigenvalue problem before thresholding rather than thresholding directly. This rotation can dramatically reduce sensitivity to noise. For some chemical systems and noise regimes, they find sample requirements reduced by up to a factor of 100, and with oracle access to the optimal rotation, up to 10,000-fold improvements are theoretically possible. They demonstrate this on the industry-relevant free NTA chelate complex, which is a meaningful benchmark for real-world quantum chemistry.
There was a very interesting paper on quantum superresolution and noise spectroscopy from Gardner and colleagues that connects quantum computing to sensing applications. Can you explain the connection they draw?
This paper is a lovely example of quantum computing enabling quantum sensing rather than the other way around. The problem is detecting a weak, incoherent signal when both signal and noise are imprecisely known. This is the canonical superresolution and noise spectroscopy problem. Gardner and colleagues show that quantum algorithms like weak-Schur sampling, density matrix exponentiation, and quantum signal processing can test properties of the unknown quantum state, its rank, purity, spectral gap, faster than full-state tomography. They apply this to a remarkable range of physical problems, detecting exoplanets, stochastic gravitational waves, ultralight dark matter, and even geoentropic quantum gravity. It's a beautiful demonstration that quantum computing can accelerate searches in fundamental physics.
The fully integrated quantum frequency processor on silicon from Chandra and colleagues seemed like a major photonics milestone. What makes it significant?
This is genuinely a landmark result in integrated photonics for quantum computing. Frequency bin encoding has been known to be powerful, it's high-dimensional, parallelizable, and telecom compatible, but until now you couldn't integrate all the necessary components on a single chip. Chandra and colleagues monolithically integrate a biphoton frequency comb source, a pump rejection filter, high-speed phase modulators, and a programmable pulse shaper all on a 4x7mm silicon chip. They demonstrate tunable frequency beam splitters with over 94% success probability, synthesize arbitrary single qubit gates, and perform the first on-chip frequency bin quantum state tomography of a Bell state with 95.7% fidelity. The scalability to more frequency modes on the same platform makes this a credible path toward large-scale photonic quantum processors.
The encrypted cloning paper from Yamaguchi and colleagues is conceptually fascinating. They're essentially refining the no-cloning theorem. What's the actual claim?
This paper makes a subtle but important conceptual point. The no-cloning theorem says you can't copy an unknown quantum state, but encrypted cloning shows that you can spread quantum information into many copies if those copies are simultaneously encrypted with a single-use decryption key, meaning no individual copy is accessible without the key. The open question was whether this is stable under hardware noise. They settle it experimentally on IBM Heron R2 processors with up to 154 qubits, showing that encrypted cloning is robust even when used in parallel, series, or interleaved configurations while preserving pre-existing entanglement. The refined understanding of no cloning is quantum information can be spread without dilution or degradation, but the decryption mechanism must be single-use. It has implications for quantum secret sharing and distributed quantum computation.
The classical verification of quantum computation paper from Kalai, Khurana, and Razes seems to solve a long-standing open problem. Can you break down what they achieved?
This is a significant theoretical cryptography result. The challenge is, how can a classical verifier check that a quantum prover is actually running a quantum computation correctly using only one copy of the QMA witness? Previously, classical verification protocols consumed the witness state, and since QMA witnesses can't generally be cloned, you'd need many copies to amplify soundness. Kalai and colleagues construct a protocol that uses a single copy of the witness, achieves negligible completeness and soundness errors, and does not destroy the witness. The security relies on the post-quantum learning with errors assumption. The key technical tools are a state-preserving classical argument for NP and dual-mode trapdoor functions with state recovery. This is a major step toward practical classical verification of quantum advantage claims.
There was also the paper on quantum error characterization using tangent space decomposition from Perego and colleagues. How does that advance our ability to diagnose errors on real hardware?
This is a practically valuable contribution to quantum device characterization. Standard benchmarking assumes Markovian time-independent noise, but real devices have coherent miscalibrations and temporally correlated fluctuations. The tangent space decomposition approach treats small imperfections as perturbations of the target quantum map, decomposing them into coherent Markovian and non-Markovian components from a single tomographic snapshot. They validate this on a trapped calcium-40 ion, injecting controlled slow fluctuations and showing they can quantify non-Markovian effects. The ability to diagnose all three error types simultaneously from one measurement is a significant practical advantage over methods that require separate characterization protocols for each error type.
The differentiable maximum likelihood noise estimation paper from Tao and colleagues for quantum error correction seemed like a very practical tool. What's the improvement over existing methods?
Decoding performance in QEC depends critically on having accurate noise parameters, but estimating those parameters from syndrome data has been a challenge. The DMLE framework from Tao and colleagues makes syndrome log likelihood computation fully differentiable, so you can optimize noise parameters directly via gradient descent. For surface codes, they use a novel tensor network architecture with optimized contraction paths to make this tractable even for distance 5 codes with 25 rounds. On Google's experimental data, they reduced logical error rates by up to 30.6% for repetition codes and 8.1% for surface codes compared to previous state-of-the-art methods, including reinforcement learning approaches. The key advantage is that it's provably optimal and decoder independent. It gives you the best possible noise priors regardless of which decoder you use.
The Adaptive Aborting Schemes paper from Pambay and colleagues for QEC decoding is an interesting systems-level optimization. What's the core idea?
The insight is elegantly simple. If early syndrome measurements already indicate a shot is going to result in a logical error, why keep measuring? Current QEC controllers run all scheduled syndrome rounds regardless. The Adaptive Abort module monitors syndrome data in real time and terminates shots early when they look risky, before spending more resources on them. This reduces the decoder's workload and suppresses logical error rates simultaneously. Their add-abort scheme substantially outperforms both fixed depth and one-step look-ahead approaches. For color codes at distance 15, they achieve 60% improvement in decoder efficiency. As code distances grow, the gains increase, which is exactly the right scaling behavior for future large-scale fault-tolerant systems.
Let me ask about the qubit reset paper from Lejeune and colleagues using the Mpemba effect. That's a very unusual connection to make.
It's a delightful paper that exploits a counterintuitive phenomenon. The Mpemba effect is the observation that hotter systems can sometimes cool faster than cooler ones. The authors show that you can exploit an analogous effect in qubits to speed up passive reset, the process of letting a qubit relax to its ground state. The trick is a single entangling 2-qubit gate that converts local single-qubit coherences into fast-decaying global 2-qubit coherences, removing their overlap with the slowest decaying mode of the system. For realistic parameters, where coherence times exceed energy relaxation times, this reduces reset times by up to 50%. They demonstrate this on an IQM superconducting processor. Since passive reset is a significant bottleneck for algorithmic execution, it's much slower than gate operations. This is a practically valuable speedup.
The complementarity paper from Agarwal and colleagues, showing there's no absolute hierarchy of quantum complementarity, seems like a fundamental result about quantum mechanics itself. What's the implication?
This is a beautiful foundational result. The conventional wisdom is that some sets of quantum observables are more incompatible than others. You can rank them by how sharply they can be jointly measured. Agarwal and colleagues prove a no-comparison theorem showing this ranking is not absolute. It depends on the global configuration of quantum probes. Specifically, two sets of observables can have reversed incompatibility ordering depending on whether you have identical copies or parallel anti-parallel pairs of probes. This means quantum incompatibility is not an intrinsic property of the observables alone. It depends on the global resource configuration. The result also reveals a subtle role of entanglement in shaping measurement limitations and calls for reassessing quantum information protocols under finite resources. It's the kind of result that makes you rethink basic assumptions.
The free quantum computing paper from Berent and colleagues takes a very different mathematical approach to understanding quantum computing. What's the axiomatization they propose?
This is a fascinating foundational contribution from the programming languages and category theory community instead of the standard continuous postulates of quantum mechanics, complex Hilbert spaces, unitary evolution, Born rule. They replace everything with a small number of discrete equations based on reversible classical computing. The quantum advantage is isolated in the ability to take certain well-behaved square roots of classical operations. The free model they construct is a category theoretical alternative to the standard linear algebraic model that has the same expressivity and computational universality, but additionally allows automated verification and combinatorial optimization of quantum computations. It's a programming language perspective on quantum computing that could enable brute force search to optimize quantum circuits in ways that the continuous model doesn't easily support.
The Merlin auto-formalization framework from Wren and colleagues for quantum computing proofs is an interesting AI meets quantum theory contribution. What's the significance?
Merlin is a fully automated pipeline that takes LaTeX source files from quantum computing papers, extracts mathematical statements, formalizes them into verified Lean-4 code built on MATLAB, and translates back to human-readable LaTeX. They evaluate it on 3 theoretical quantum computing papers, producing over 2,000 Lean declarations from 114 statements. The significance is twofold. It provides machine-verified peer review, catching errors that human reviewers might miss, and it generates high-quality synthetic data for training future reasoning models. The fact that it achieves end-to-end formalization on complete research papers, not just toy examples, is a meaningful milestone. As quantum computing theory becomes more complex, automated verification tools like this could become essential infrastructure.
The quantum audit benchmark from Afane and colleagues evaluating LLMs on quantum computing knowledge is timely. What did they find about current model capabilities?
The results are sobering in an important way. Top models like Claude Opus 4.5 reached 84% accuracy, exceeding the expert human average of 74%. But there's a 12-point accuracy drop on expert written questions compared to LLM-generated ones, suggesting models are better at answering questions that look like they're training data. More concerning, models frequently accepted and reinforced false premises embedded in questions rather than identifying them, with accuracy below 66% on these critical reasoning tasks. Performance also dropped to 73% on security questions. The benchmark covers 2,700 questions, including open-ended and false premise questions, which is a more rigorous evaluation than pure multiple choice. The takeaway is that LLMs are useful tools for quantum computing education, but should not be trusted for rigorous technical reasoning without verification.
The Halo Quantum Operating System paper from Ye and colleagues addresses a very practical problem: resource sharing on quantum cloud platforms. What's the key innovation?
Halo tackles the fundamental mismatch between high user demand and scarce quantum hardware. Currently, quantum cloud platforms use fair share scheduling with no way to multiplex jobs simultaneously, leaving many qubits idle. Halo introduces 2 mechanisms: a hardware-aware qubit sharing algorithm that places shared helper qubits in regions that minimize routing overhead and crosstalk between different users' processes, and a shot adaptive scheduler that allocates execution windows based on each job's sampling requirements. On IBM Torino, they achieve up to 2.44x improvement in hardware utilization and 4.44x throughput increase, with fidelity loss kept within 33%. It's a systems contribution that could significantly reduce the queue times that currently frustrate quantum cloud users.
The qt quantum database paper from Chen and colleagues is an ambitious vision, treating quantum computation as a first-class database execution option. Is this realistic near term?
It's a vision paper with some concrete preliminary results, which is an important distinction. They compile an extended SQL into gate-efficient quantum circuits, use a hybrid optimizer to choose between quantum and classical execution plans, and introduce selective quantum indexing and fidelity-preserving storage. Their deployment on a real quantum processor shows it can outperform classical baselines at scale for certain query types. The honest assessment is that this is early stage. The quantum advantage is limited to specific query patterns where quantum speedups are theoretically justified and the hardware constraints are significant. But the 3-stage evolution roadmap they propose is thoughtful, and the open source release makes it a useful research platform. It's a credible first step toward quantum native databases.
The passive environment-assisted quantum communication paper from Voss and colleagues on bosonic channels is quite theoretical. What's the practical upshot?
The fundamental problem they address is that a bosonic pure loss channel, like essentially transmission through a beam splitter, has 0 quantum capacity when transmissivity is below 50%. This is a hard physical limit that seems to prevent quantum communication over lossy channels. The key insight is that by choosing the right input state for the ancilla port of the beam splitter, what they call passive environment assistance, you can recover quantum communication capacity even below the 50% threshold. Ideal GKP states enable perfect transmission at arbitrarily small transmissivity, but those are experimentally challenging. They explore more accessible alternatives like Fock states, cat states, and squeezed cat states, and find good analytical encoding and decoding schemes. This is relevant for quantum networking over lossy fiber links where transmissivity naturally falls below 50%.
The CatCode logical state preparation paper from Chen and colleagues seems like an important practical contribution to bosonic error correction. What makes their approach notable?
Preparing arbitrary logical states fault-tolerantly is a major challenge for any error correction code, and bosonic codes like the CAT code are no exception. Chen and colleagues present a complete framework for fault-tolerant preparation of arbitrary logical states in the four-legged CAT code that specifically suppresses the dominant incoherent errors, excitation, decay, and dephasing in both the bosonic mode and the ancilla through error detection. Their numerical simulations with realistic superconducting cavity parameters yield logical infidelities around 10^4, and the scaling analysis confirms quadratic suppression of the physical error rate, meaning all first-order errors are eliminated. The protocol is compatible with current 3D superconducting cavity hardware and scalable to multiple bosonic modes. This is a concrete path to magic state preparation for bosonic quantum computing.
Stepping back, what do you see as the overarching themes across February 2026's research? There's clearly a lot happening simultaneously.
I see four major threads weaving through this month's work. First, the maturation of quantum error correction from theory to practice, the quantinuum beyond break-even result, the Pinnacle Architecture, the adaptive abort schemes, and the noise estimation tools all point to QEC becoming an engineering discipline rather than just a theoretical one. Second, quantum networking is moving from lab demonstrations to real-world infrastructure as shown by the PAN Group's repeater milestone, the NYC entanglement swapping, and the Berlin teleportation over deployed fiber. Third, there's a growing sophistication in understanding quantum resources, magic, complementarity, and entanglement, with both foundational results like the no comparison theorem and computational hardness of magic, alongside practical implications for algorithm design. And fourth, the quantum software and systems stack is maturing, with contributions ranging from quantum operating systems and databases to auto-formalization and LLM benchmarking. The field is genuinely becoming multi-layered.
That's a great synthesis. One more area I wanted to touch on, the quantum machine learning and variational algorithm papers. There were several addressing barren plateaus, robustness, and automated QML. Is there a coherent story there?
The QML story this month is one of growing maturity and honest reckoning. The comprehensive barren plateau study from Hashimoto and colleagues provides a systematic numerical characterization of how barren plateaus and overparameterization interact, giving practitioners concrete guidance on circuit design. The automated QML paper from Rybacki and colleagues shows that AQML-generated circuits can outperform manually designed ones for remote sensing data fusion tasks, suggesting automation is a viable path forward. The fundamentals chapter from Pira and Ribbentrop on QML robustness connects adversarial robustness to the physical principles of quantum systems, which is an important conceptual bridge. And the Hyper-Q privacy paper from Ngo and colleagues shows that quantum noise can actually be a resource for differential privacy. Together, these paint a picture of QML becoming more rigorous and application-aware, even as fundamental questions about quantum advantage in learning remain open.
This has been a really illuminating conversation, Bob. February 2026 feels like a month where the field simultaneously pushed theoretical boundaries, from the hardness of magic to the no comparison theorem, while also delivering concrete engineering milestones in error correction, networking, and systems. It's exciting to see the full stack coming together, even if there's still a long road to broad quantum utility.
Well said. What strikes me most is that the gap between theory and experiment is narrowing faster than many expected even a few years ago. The Pinnacle Architecture's 100,000 qubit RSA factoring estimate, the beyond break-even logical qubits on Helios, the quantum repeater milestone from Pan's group, these aren't incremental improvements, they're qualitative shifts. The honest caveat from Proctor and colleagues remains important. We're not at quantum utility yet, and the remaining engineering challenges are formidable. But the trajectory is genuinely encouraging. February 2026 will likely be remembered as a month when several pieces of the puzzle clicked into place simultaneously.